welcome to the seminar. This is the seminar for the spectral-algebro-geometry. Today our speaker is Matteo Doni. He will introduce us the Tannaka duality for the quasi-geometry stacks. Thank you.
Thanks. Okay. First, I recall something from the last talks. Okay. We start with because in the first talk of this seminar I spoke about Tannaka duality in the maybe categorical with a categorical meaning, means categorical version. Here is more geometric version, some algebraic version. So we need to add something about my first talk. Actually, in this talk, which is the second one of this seminar, Krishna say something about that in the end, but I recall something of his talk. For example, time 25, okay, about he introduced moduli theory, and he said that idea of moduli theory is the following. Can we classify the isomorphism classes of mathematical object of a given type. Okay, and moreover, he say that moduli space is a space whose points are in natural bijection with isoclasses of a given algebro-geometric object. In the end of my talk, my first talk, which is the first of this seminar, I say that we need the stacks in some sense to have the geometric version of the Tannaka duality, and indeed Krishna in his talk said that in order to solve the problem linked with the moduli theory, we use stacks. Okay, in some sense introduce it, and in particular in the first talk, in some sense actually it works. Okay, we proved what? We proved that if we have a G an algebraic group, we have a bijection from map from the affine group A at K algebra, affine group over K. We have a bijection between the image of J via A and such functor made in this way. Plus some axioms. So, what is the point? The point is that it is well known that actually GA are A points of G. Okay, so in the sentence in the above blackboard, I say that in some sense a moduli space is a space whose points are in natural bijection with isomorph classes of a given algebra-geometric object, but here, okay, we work with point of G, but so in some sense, whose point, okay, so we have point, but the algebra-geometric object is not actually G, but is in some sense the point is that, okay, what is it, a point here? A point is simple amorphic okay, is simply amorphous in this way, but we don't consider the fact that G is actually a group, so we lose some of the property of G. So we need to work with stacks. Okay. I want to say that actually here we don't want a point of G. Okay. But here I can say we want okay, a point of a classifying space of G, okay, which is a unstack in the classical case, okay. But in our talk, it will be an infinity stack or actually a quasi-geometric stack, okay. So the point that we need a point of the unstacks. Moreover, okay, in my first talk, I proved that, or maybe I say something about the fact that rep G actually are G modules, okay. So here we need point in a stacks in some sense. Here we have morphism with some axioms, okay, between modules. Now we want to translate this theory in the spectral theory, and from the talk of Krishna we know that in the setting of infinity stars, maybe, okay, the G modules, the modules are actually the quasi-coherent. So instead of here rep G or G mod, we want quasi-coherent sheaf for, in this case, for PG, okay? Okay, and here we have modules, but in the same way we want, okay, quasi-coherent sheaf of something, and in this case of spec A. Another things we consider spec A as stacks in this case, okay? And last things that we want in order to generalize here, okay, last things. Here we have BG, okay, and here spec A. So, but we know that we can find quasi-coherent sheaf, the infinity category of quasi-coherent sheaf, not only for BGA or affine affine things, okay, but we want to work with more general things here, okay. So we want a stacks, and here we say, and here two are general stacks, okay, and here is in our table we will have quasi-coherent sheaf of a stacks BG X sorry, and here Y. Okay, so here is the way we generalize the categorical version of Tannaka duality. So, and I remember that it is important that here we have some axioms. Okay. Now, I have already lose, no, here. In this talk in particular, we want to prove, but I won't prove this theorem, I only say something about it, the Tannaka duality for quasi-geometric stacks. And now I state this theorem, let x, y, two functors, from the connective A infinity rings to S. This is the category of the infinite category of space. I won't say that they can be big, okay? Not this is not the category of small spaces. The functors, and such that x is quasi-geometric stacks. Okay. And y is representable by a quasi-compact quasi-separated spectral spaces is let fun we define this category quasi-coherent. Okay. This is the infinity category of symmetric monoidal functors.
Sorry, what is the spectral space?
Sorry, what is it?
What is the spectral space?
The spec
Spectral space.
spec no, sorry.
Yes,
In space?
please. What do you mean?
Space?
Yes. Spectral space. What is spectral space?
I actually I don't know. I won't be honest. The point, this is a general theorem, okay? I stated this theorem, but actually for us, sorry, here we want y. The point is that for us y is quasi geometric stacks. Okay.
Okay.
I found it too difficult attack this theorem in its generality. So we will see only a really weak. We will see a weak theorem. Okay. Or spectral space. So functors. Then the construction. Pullback. now we have this construction, okay? I have to send a morphism in this pullback, and the essential map of this, I don't say, so whose essential image is spanned by those symmetric monadal factor F such that they satisfy these four property F admits right adjoint G, in other words, F preserves small colimits. This because quasi-current, the category of quasi-current is presentable, the physical category is presentable, and B F carries connected objects in connected objects. C G preserves small coordinates and D each object F and G the canonical map is an equivalence. Okay. So this is the theorem in its generality. I would say that I want only remark something about this theorem. First of all, that is in the generality that I spoke before, okay? And another thing I forgot before, that I want to only say that to end not about stacks, there is the proof of this theorem. So to end not about stacks, chapter 7.2, okay? And another thing is that in the, I think, next talk we will spoke about geometric stacks, and in geometric stacks we will use geometric stacks to delete the dependence from G of these features, okay? And I want only recall that okay, so I recall only something about Rujvan talk. Okay. Definition. A quasi-geometric stacks is a functor actually is for this moment is in the big category of spaces, in the category of big spaces, which satisfy descent with respect to FBC topology, with respect to this topology, B, the diagonal is quasi affine, and C exists a infinite ring and faithfully flat morphism spec AS, and moreover And moreover, this is an example. Which is 9.1.1.7 in seg, or in ρ1 torque time 33. Okay. Let R be a commutative ring and let G be a flat affine group schemes over R declassifying stars of G denoted BG is quasi-geometric. Okay. And yes, I want to only record these two things. And now I a short last remark about this theorem before I write a specific situation of this theorem. Okay, is that this is an infinity group or a space, okay, and here we have an infinity category, but actually the point is that the essential image is a space, okay? So the y point of x classify this factor in some sense up to homotopy equivalence, okay? Okay, so we can write the less general situation. Questo. No. Okay. This is in SG proposition 9.2.2.1. Okay. So let x, y functors such that the diagonal map of x is quasi-affine. So in particular, quasi-geometric stars have this property. Okay. Then canonical map the same map of before. Is fully fixed. Okay. This, in this case, is the infinity category of geometric monoidal functor. Okay. Other time, this is a space. So from this fact and the fact that it is fully faithful, in particular, for and pair of maps FF1. Okay. Then these maps we can see something else. Yeah. Maybe I can recall this map. Let's send F in the pullback. Okay. Map. Then any. Okay. Quasi-coherent linear symmetric monoidal natural transformation alpha is an equivalence. Okay. This is a general situation. Sorry before I say that was a specific one, but actually this theorem is the generalization. And indeed, we don't have a characterization of the essential image of this factor, okay, these maps. And I want to only say that in Krishna in case I recall at the start point of this talk, I say that we work up to isomorphism, but actually here we are in infinity category theory, so we work up to equivalence. Okay, that's a point. This is the difference between one stacks and infinity stacks in some sense. And so before prove this theorem, or at least say something about this theorem, I want to try to say how we recall, we find the classical Tannaka duality from this theorem, okay, this proposition. The first remark is very natural. X quasi-geometric stacks implies the diagonal is quasi-affine, and so this is the first point. Second, the classification stacks, okay, is quasi-geometric, so its diagonal is quasi-affine. So we can use this theorem with BG instead of X. Okay, this is the first point. I have another time if you want to make a break, or I can go. Yeah. So okay, we have these two remarks. Now let K be a field G be an affine schemes over K let A be a algebra okay from this fact, okay, from this we actually have that BG as a canonical, we call it as epsilon, a canonical base point, and we denote epsilon A, okay, so this is a K algebra, implies that we have isomorphism, but we denote with epsilon A this composition. Okay. Luri in his book called this proposition weak Tannaka duality. So from the above proposition, we have that from the above proposition, we have that map D spec A BG quasi-coherent mod A. Okay. We have that this map is fully is that fully so ciao. Dai, vieni 5 minuti la faccio. So, yes, so we are in this situation. In particular, that means that, okay, map is a very strange notation. Map PG epsilon A is equivalent. So I remember that this and epsilon A in the pullback. Okay. So is equivalent to map epsilon star epsilon, oh, sorry, to this, and in particular this is okay, this is from the result. Okay, so with some computation it is possible to prove that this is actually this morphism with this tensor. That means that is a morphism between groups in some sense, and this is equivalent to GA, where this is classical. You send a morphism F in point F1, okay, and you send an object G in the morphism that send E in E times G, so the multiplication for G, okay, and in the first talk I call this, not in this way, but as something similar. And this is the classical situation, okay? Actually, is because we have the cover GA, okay? That's but actually, this is not the classical Tannaka duality because in our first talk I said that we had some finiteness condition because we work with finite linear representation. Okay, so this is okay. This is only to say something. Corollary in sub 9.2.2.2. Okay, that's not really important. Is almost our starting classical Tannaka duality. Lux. What is the problem? The problem is that we need some finite condition. Okay. And the point that is we need we define what is it the infinity category of linear representation of G. This is okay. Actually, subcategory of quasi-current shift, which is full. This is the quasi-current shift, which is which are locally free. Of finite rank. Okay, so this is the point that we work in general situation, but we starting from a different situation to this condition. Sorry. In particular, epsilon A restrict to mod LF. We define this in our first talk, and you can denote this by E, and we find really our starting situation, because if we restrict to this subcategory of quasi-current, we find that GDA is equivalent to automorphous. Okay. This is, I define this in the first talk. Okay.
So a representation of the G is defined for subcategory of the quasi-geometric. I mean, the representation of the G is you are defining this category as the first subcategory generated by a local differential.
See, yeah. Sorry. Maybe I can write back there. Okay. Rapid G. Okay, rapid G is the full subcategory spanned by quasi-current shifts which are log 3 of finite. Okay, actually you can define these in this way, okay, but if you define Rebbe in the classical way, you discover that this subcategory is in a sense classified by these shifts, generated by this shift, okay? And we find the starting situation, but okay, we can make another remark about this proposition. This we can multiply it. So I can leave it here. Some remark about this situation. Okay, the first is that, okay, I will say something about the proof, but I want to say that in the proof, is not necessary that epsilon A, which is a morphism this way, factor, I can say factor to spec K, okay? So this is not necessary. So we can make the same. Okay. Yes. Indeed, in this situation, I never write K in some sense. Okay. You can start with U spec A, BG, and V spec A, BG. Okay, and in some sense, you can make this change, and all the things work, okay, in the same way. This is interesting because when we work over a field or something like a commutative ring, we actually do derive algebraic geometry, but actually SEG is a bit general at derive algebraic geometry, because we work without a linearity in some sense. Okay, it's not. Okay. I want to say only 3 consequences of this theorem. Okay, 3 consequences. I want to say that in particular, I don't prove this consequence. I only say the consequence. Okay. So the first thing is that let X be a quasi-geometric start, then X is hyper complete sheaf. Okay, with respect to this topology, okay, that's okay. In the last talk, Rushan spoke about hypercomplete stacks, if I remember well. Yeah, and this is important because in some sense means that homotopy group detect equivalence, okay, and in other words, Whitehead theorem holds in this situation, okay? In some sense, first consequence. The second one is that until now we have this fact that if we have x be quasi-geometric stack, as a consequence, for each object of this infinity category, xa is essentially I want to only say that this follows from the fact that this is a typical situation when you use two facts to prove this, that in some sense, if someone, when you work with double infinity category theory, preserves small colimits is linked to preserve compact object and the category if we have okay, we can define for every infinity category the category of compact object with respect to some cardinal, and this category is essentially small. This is important because until now we work with big spaces, but we can delete these, okay? And actually when we work with the quasi-geometric stack, we work with functors that land in the infinity category of small spaces. And the last thing is that 3. If we have two quasi-geometric stacks, okay, if f is a functor between the category of quasi-coherent sheaves, and this functor is the exact symmetric monoidal equivalence, then f is equal a small f pullback for some equivalence. In this way. And I want to say, I'm not sure that we will use this part, but it's useful. In particular, this derives from the fact that the physical theory of quasi-current shift have a really nice T-structure, to some sense, that with good behaviors with respect to small colimits. And so, that's all. I'm finished.
Thank you, our speakers. Thank you, our speaker, and his wonderful talk. Are there any questions on site or online? If there are no questions, let us thank our speaker.
Okay.